Right now, at this very moment, a star is moving toward us. It is not a metaphor. It is not a thought experiment designed to illustrate some abstract principle. It is a real physical object, a sphere of burning hydrogen, roughly 60% the mass of our Sun, falling through the galaxy on a trajectory that will carry it directly into the outermost boundary of our solar system. Its name is Gliese 710. It sits in the constellation Serpens Cauda, the tail of the serpent, about 62 light-years from Earth, and it is getting closer. Every second that passes, every heartbeat, every breath, Gliese 710 moves approximately 14 kilometers nearer to our Sun. That is roughly 50,000 kilometers per hour. At that rate, it covers the distance from the Earth to the Moon in about 8 hours, and it has been falling toward us for millions of years. Most people have never heard of it. It does not appear in emergency briefings. It does not generate headlines or trigger national security meetings. You will not find it trending on any platform. And yet, among astronomers who study the long-term dynamics of stellar motion, Gliese 710 is one of the most carefully watched objects in the sky. Not because of what it is, which is by stellar standards and entirely ordinary, but because of what it will do when it gets here. In approximately 1.3 million years, this quiet, dim orange dwarf star will pass through the Oort Cloud, the vast spherical shell of frozen objects that envelops our solar system at distances of up to 100,000 astronomical units from the Sun. And when it does, it will disturb trillions of dormant comets, sending an unknown number of them cascading inward, toward the inner solar system, toward the rocky planets, toward Earth. The distance of closest approach is currently estimated at roughly 10,000 to 13,000 astronomical units. 1 astronomical unit is the distance from the Earth to the Sun, about 150 million kilometers. So 10,000 astronomical units sounds far. It sounds safe. It sounds like something we can afford to ignore. But the Oort Cloud extends out to 100,000 astronomical units. The star will not brush past the edge of this structure. It will plunge deep into it. It will pass through a region where the density of frozen objects is far higher than at the cloud's outermost fringe, and the gravitational consequences of that passage will ripple inward for millions of years, long after the star itself has moved on. We know this because of a spacecraft called Gaia, launched by the European Space Agency in 2013. Gaia has mapped the positions and motions of nearly 2 billion stars with astonishing precision. And when astronomers used that data to trace the future trajectories of nearby stars, one result leaped out from the rest. Gliese 710 was not just heading in our general direction. It was aimed, with unsettling accuracy, directly at the heart of the Oort Cloud. The earlier estimates, based on the less precise Hipparcos satellite, had placed the closest approach at about 70,000 astronomical units. Gaia shrank that number to roughly 13,000. The threat was not distant, it was deep. This is a story about patience, cosmic patience, the kind of patience that measures time, not in years or centuries, but in epochs, the kind of patience that allows a threat to develop so slowly that no single human lifetime can perceive it. Gliese 710 will not arrive tomorrow. It will not arrive in 1,000 years. It will not arrive in 100,000 years. But it will arrive. And when it does, it will set in motion a chain of events that may reshape the conditions of life on this planet for millions of years to come. By the end of tonight, you're going to understand what Gliese 710 is, where it came from, how we discovered its trajectory, and why astronomers consider it the most significant stellar encounter our solar system will face in the foreseeable future. You will learn about the Oort Cloud, the invisible structure that surrounds our solar system like a vast, fragile shell. You will see how the gravitational influence of a passing star can transform that shell from a dormant reservoir into an active source of cometary bombardment. And you will confront the unsettling possibility that events like this have happened before, that they have shaped the history of life on Earth, and that the next one is already on its way. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. This is the story of the slowest collision in the solar system, a meeting between two celestial bodies that is already underway, that will take more than 1,000,000 years to unfold. And that carries consequences we are only beginning to comprehend. It is a story about the fragility of the place we call home and the invisible architecture of ice and gravity that surrounds it. It is a story about what happens when that architecture is disturbed. Now, let's begin. To understand what Gliese 710 means for our future, we first need to understand the architecture of our solar system, not the familiar architecture of planets and moons, but the deeper architecture, the hidden structure that stretches far beyond anything we have ever visited with a spacecraft. We need to understand the Oort Cloud. Most people know the basic layout of the solar system: the Sun at the center, Mercury, Venus, Earth, and Mars in the inner region, the asteroid belt, then the gas and ice giants, Jupiter, Saturn, Uranus, and Neptune. Beyond Neptune lies the Kuiper Belt, a band of frozen debris where Pluto and thousands of similar objects orbit between roughly 30 and 55 astronomical units from the Sun. The New Horizons spacecraft, which flew past Pluto in 2015, gave us our first close-up look at this distant region. It was cold, barren, and strikingly beautiful. Most people assume that the Kuiper Belt is where the solar system ends. It is not. The solar system extends far, far beyond the Kuiper Belt, and the structure that fills that vast outer volume is the Oort Cloud. The Oort Cloud was first proposed in 1950 by the Dutch astronomer Jan Hendrik Oort. He was studying long-period comets, those comets that take thousands or even millions of years to complete a single orbit around the Sun. These comets posed a puzzle. Their orbits were so elongated that they extended far beyond the known planets, out to distances of tens of thousands of astronomical units. And they arrived from every direction, not just from the plane of the solar system where the planets and the Kuiper Belt reside, but from above, below, and every angle in between. This was strange. The planets and the Kuiper Belt are all confined to a relatively thin disk, but the long-period comets came from a sphere. Oort proposed that the outermost solar system must contain a vast, roughly spherical reservoir of icy bodies, extending from roughly 2,000 to perhaps 100,000 astronomical units from the Sun. These objects, he argued, were remnants of the original cloud of gas and dust that had condensed to form the solar system 4.6 billion years ago. During the early, chaotic period of planetary formation, gravitational interactions with the giant planets, especially Jupiter and Saturn, had scattered enormous numbers of icy planetesimals outward from the inner solar system. Some escaped entirely, flying off into interstellar space, but many were captured into extremely distant orbits, forming a spherical shell around the Sun. There, in the cold and darkness, they had remained for billions of years, slowly orbiting, slowly drifting, waiting. No one has ever directly observed the Oort Cloud. That statement bears repeating, because it is important and somewhat astonishing. We have never seen it. No telescope, no matter how powerful, has ever imaged a single Oort Cloud object in its native orbit. Every comet we have studied from this region was only detected after it had already been dislodged from its orbit and sent falling inward toward the Sun. The Oort Cloud is entirely inferred. It is deduced from the properties of long-period comets, from the physics of planetary formation, and from our understanding of how gravity works at very large distances. And yet, the evidence for its existence is so compelling that virtually no astronomer doubts it. The scale of this structure is almost impossible to convey, but let us try. Consider this first comparison. If we shrink the solar system so that the distance from the Earth to the Sun, 1 astronomical unit, becomes a single step of about 1 meter, then the entire inner solar system, from Mercury to Mars, fits within about 2 meters. Jupiter sits 5 meters away. Neptune sits 30 meters away. The Kuiper Belt extends to about 50 meters. But the outer edge of the Oort Cloud is 100 kilometers away. 100 kilometers. You could walk across the inner solar system in seconds. You could jog past all the planets in a minute. But to reach the edge of the Oort Cloud, you would need to walk for an entire day without stopping. The Oort Cloud is not a nearby frontier. It is a vast, empty, frozen wilderness that dwarfs everything we think of as the solar system. Here is a second way to grasp the distance. Light, the fastest thing in the universe, moves at approximately 300,000 kilometers per second. It crosses the distance from the Sun to the Earth in about 8 minutes and 20 seconds. It reaches Mars in roughly 12 minutes. It passes Neptune in about 4 hours and 10 minutes. But to reach the outer edge of the Oort Cloud, light needs approximately 1.6 years. The Oort Cloud is so large that it is measured not in light minutes or light hours, but in light years. Its outer boundary extends a meaningful fraction of the way to the nearest star. In fact, the outer edges of our Oort Cloud may overlap with the outer edges of Alpha Centauri's equivalent structure, if it has one. The solar systems of neighbouring stars are not cleanly separated. At their farthest reaches, they blur together like the suburbs of adjacent cities, with no clear boundary between one and the next. And here is a third comparison, one that reveals just how thin and fragile this structure is. Imagine the entire Oort Cloud compressed into a sphere the size of the Earth. If you did that, the combined mass of all its objects would form a layer thinner than a coat of paint spread across the surface. Despite containing an estimated 1 trillion to 100 trillion objects, the Oort Cloud is fantastically diffuse. The average distance between neighbouring objects is enormous, measured in millions of kilometres. It is not a wall, it is not a shield, it is a mist, a barely there haze of frozen debris scattered across an almost inconceivable volume of space. The objects within the Oort Cloud are individually small. Most are thought to be irregular chunks of ice and rock, ranging from roughly 1 to perhaps 20 kilometers in diameter, though some may be larger. The composition is similar to the comets we observe in the inner solar system. Water ice, frozen carbon dioxide, ammonia, methane, and a mixture of silicate dust and organic molecules. Some may contain complex hydrocarbons and amino acids, the building blocks of life, preserved in a deep freeze for billions of years. Their surfaces are dark, coated in radiation-processed carbon compounds that have been slowly altered by cosmic rays over the eons, exposed to the faintest trickle of ultraviolet radiation from distant stars and to the constant bombardment of galactic cosmic rays. Their surface chemistry has been gradually transformed into a dark, reddish crust of complex organic polymers called tholins. Their temperatures hover just a few degrees above absolute zero, around negative 268 to negative 270 degrees Celsius. They are among the coldest, most pristine, and most ancient objects in the solar system. Time capsules from the era of planetary birth. These objects orbit the Sun, but slowly. An object at 50,000 astronomical units from the Sun takes roughly 10 million years to complete a single orbit. An object at 100,000 astronomical units takes even longer. These are not dynamic orbits. They are barely orbits at all. The objects drift in the outermost reaches of the Sun's gravitational influence, held in place by the most tenuous possible gravitational grip. At those distances, the Sun's gravity is extraordinarily weak. It is only about 1/10,000,000th as strong as it is at Earth's distance. Even a very gentle external force, a subtle gravitational tug from a passing star, a slow torque from the galaxy's tidal field, can be enough to alter an Oort Cloud object's orbit significantly. This is the key. This is why the Oort Cloud matters for the Gliese 710 story. Because these objects are so weakly bound, they are exquisitely sensitive to perturbation. They are like a house of cards balanced on the edge of a table. The slightest vibration can send them toppling, and when they topple, some of them fall inward, toward the Sun, through the planetary region, past the orbits of Jupiter and Mars and Earth. When they arrive, heated by the Sun, their ices vaporize, producing the spectacular tails that we see as comets. Every long-period comet is a former Oort Cloud object. Every one is a piece of the outer solar system that was shaken loose by some external disturbance and sent tumbling into the inner realm. What causes these disturbances? There are two primary mechanisms, and both are constantly at work. Understanding them is essential, because Gliese 710's impact will be layered on top of processes already in motion. The first is the galactic tide. The Sun does not sit motionless in the Milky Way. It orbits the center of the galaxy at a distance of roughly 26,000 light-years, completing one full orbit every 225 to 250 million years. That orbital period is sometimes called a galactic year, and the Sun has completed roughly 20 such orbits since the solar system formed. As the Sun orbits, it does not travel in a perfectly flat circle. It oscillates up and down through the galactic plane, the dense, star-rich midplane of the Milky Way's disk. This vertical oscillation takes roughly 60 to 70 million years per full cycle. The Sun is currently about 50 to 80 light-years above the galactic midplane and moving upward. This oscillation matters because the gravitational field of the galaxy is not uniform. The midplane is denser, packed with more stars, gas, and dust. When the Sun passes through or near the midplane, the ambient gravitational field is stronger. When it rises above or dips below, the field weakens. This changing field exerts a slow, steady torque on the outermost Oort cloud objects. The effect is subtle, but relentless. Over millions of years, the galactic tide gradually twists and rotates the orbits of Oort cloud objects. Some of those rotated orbits become elongated enough to carry the objects into the inner solar system. This process produces a steady, low-level drizzle of long-period comets, perhaps one or two new ones entering the inner solar system each year. It is the background hum of cometary activity, always present, always operating. Think of the galactic tide as a gentle breeze blowing through the house of cards. It does not knock the cards down all at once, but it keeps them trembling, always on the edge of falling. The second mechanism is stellar encounters. The Sun is not alone in its journey around the galaxy. It is surrounded by other stars, all moving on their own orbits, all drifting relative to one another. The local stellar neighborhood is not static. It is a flowing river of stars, each one tracing its own path through the galaxy's gravitational field. Occasionally, sometimes every few 100,000 years, sometimes more often, a star passes close enough to the Sun that its gravity reaches into the Oort cloud and perturbs the objects there. The effect of a stellar encounter depends on several factors. The mass of the passing star matters. A more massive star exerts a stronger gravitational pull. The speed of the encounter matters too. A star moving quickly relative to the Sun spends less time in the vicinity and therefore has less time to exert its gravitational influence. A slow encounter, paradoxically, can be more disruptive than a fast one, even if the passing star is less massive. And most critically, the distance of closest approach matters. Gravitational force obeys an inverse square law. If you halve the distance, you quadruple the force. A star that passes at 10,000 astronomical units exerts 100 times more force than a star passing at 100,000 astronomical units. The distance is everything. When a star passes close enough, it does not just nudge a few comets. It can reshape entire swaths of the Oort cloud. Objects on one side of the cloud, the side facing the passing star, are pulled toward it. Objects on the far side are left behind. The result is a differential gravitational effect, a tidal force that stretches and compresses the Oort cloud like a ball of dough being pulled apart. Some objects are accelerated onto orbits that carry them inward. Others are accelerated onto orbits that carry them outward, out of the solar system entirely, lost to interstellar space forever. The Oort cloud is slowly eroding, losing members with every encounter, and it has been doing so for billions of years. How many objects does the Oort cloud contain? The estimates are staggeringly uncertain. Most models suggest somewhere between 1 trillion and 100 trillion icy bodies larger than 1 kilometer in diameter. That is a factor of 100 in uncertainty, an enormous range. The lower estimates are based on the observed flux of long-period comets and the assumption that only a small fraction of Oort cloud objects are ever disturbed enough to enter the inner solar system. The higher estimates come from models of planet formation that predict a very large number of planetesimals were scattered outward during the solar system's early history. The total mass is estimated at somewhere between 5 and 100 Earth masses. If you could gather all these objects together, they would form a body considerably larger than any planet in the inner solar system. But spread across a sphere 100,000 astronomical units in radius, they are all but invisible. Over the lifetime of the solar system, roughly 4.6 billion years, thousands of stars have passed within a few light years of the Sun. Most of these passages were too distant to cause major disruption, but some were close enough to produce significant comet showers, bursts of enhanced cometary activity lasting hundreds of thousands to millions of years. and a few perhaps once every several 100 million years may have been close enough to strip away the outermost layers of the Oort cloud, entirely, fundamentally reshaping its structure. The Oort cloud we see today, or rather, the Oort cloud we infer today, is not the original. It has been sculpted by billions of years of stellar encounters and galactic tidal forces, whittled down from whatever initial state it possessed when the solar system was young. This brings us to the question of measurement. How do we know which stars have passed near the Sun in the past and which will do so in the future? The answer, as we touched on earlier, is the Gaia spacecraft. But the story of Gaia's contributions deserves fuller treatment because it is one of the most remarkable achievements in the history of astronomy. Gaia was launched on December 19, 2013, from French Guiana aboard a Soyuz rocket. It was placed at the second Lagrange point, known as L2, a gravitationally stable position about 1.5 million kilometers from Earth, in the direction opposite the Sun. This location is ideal for astronomical observations because the spacecraft can maintain a stable orientation relative to the Sun, Earth, and Moon, avoiding the thermal fluctuations and gravitational tugs that would degrade its measurements. From this vantage point, Gaia began a systematic survey of the sky, rotating slowly and scanning the entire celestial sphere repeatedly over its mission lifetime. It measured the positions, motions, brightnesses, colors, and in many cases the radial velocities of nearly 2 billion stars. Its angular resolution is extraordinary, on the order of a few tens of microarcseconds for the brightest stars. To put that in perspective, a microarcsecond is roughly the angular size of a coin on the Moon, as seen from Earth. Gaia can detect the apparent motion of a star across the sky with precision sufficient to measure a drift of just a few millionths of an arcsecond per year. It is, without exaggeration, the most precise positional astronomy instrument ever built. For each star, Gaia measures 5 astrometric quantities. 2 give the star's position on the sky at a reference time. 2 give the proper motion, the rate at which the star appears to drift across the sky, broken into 2 perpendicular components. And 1 gives the parallax, the tiny annual wobble in the star's apparent position caused by the Earth's orbit around the Sun, which directly yields the star's distance. When these 5 quantities are combined with radial velocity measurements, which can be obtained from spectroscopic observations, either by Gaia itself or by ground-based telescopes, the result is a complete 3-dimensional position and 3-dimensional velocity for the star. 6 numbers that fully describe where the star is and where it is going. Before Gaia, the best available data came from the Hipparcos satellite, launched in 1989 by the European Space Agency. Hipparcos measured about 118,000 stars with high precision and provided the first reliable catalogue of stellar positions and motions. It was Hipparcos data that first identified Gliese 710 as a potential close encounter. But Hipparcos had limitations. Its positional accuracy was roughly 1 milliarcsecond, about 50 to 100 times less precise than Gaia. And its radial velocity measurements were limited. The result was trajectory predictions with large uncertainties that made it difficult to determine whether a given star would pass at 50,000 or 100,000 astronomical units. Gaia changed this completely. With its vastly improved precision, Gaia allowed astronomers to trace stellar trajectories with an accuracy that had been previously unimaginable. Researchers could now integrate the equations of gravitational motion, forward and backward in time, over millions of years, tracking each star's path through the galaxy and identifying all close approaches to the Sun. The result was a revolution in the study of stellar encounters. Among the many stars analyzed, one stood out above all others: Gliese 710. Its trajectory was not merely close. It was, by a substantial margin, the closest predicted stellar encounter for the next 10 million years. Earlier estimates using Hipparcos data had suggested a closest approach of about 1.1 light-years. But when the team of Filip Bersky and Piotr Dybczynski at Adam Mickiewicz University in Poznan, Poland, applied the new Gaia data, the picture changed dramatically. The revised closest approach was approximately 13,300 astronomical units. Other researchers, using slightly different galactic gravitational potential models, found values as low as 10,000 astronomical units. The star would not merely graze the outer Oort cloud, it would penetrate deep into its interior. To visualize this, consider one more scaled comparison. If the Sun were the size of a basketball sitting at the center of a football field, the Earth would be a tiny grain of sand roughly 26 meters away. Neptune would be another grain, smaller still, sitting about 780 meters down the road. The Kuiper belt would extend to perhaps 1 kilometer. But the Oort cloud would stretch for over 2,000 kilometers in every direction. And Gliese 710, at closest approach, would be about 200 kilometers from the basketball, deep inside the cloud, surrounded by trillions of frozen objects, not at the edge, not skimming past, but plunging through the interior like a stone thrown into still water. Here is one final way to feel the vastness involved. If you could drive a car at highway speed, say 100 kilometers per hour, non-stop, day and night, without ever refueling or resting, it would take you roughly 170 years to reach the Sun from Earth. It would take about 5,000 years to reach Neptune. But to reach the outer edge of the Oort cloud, you would need to drive for roughly 170 million years. That is longer than the entire age of the dinosaurs. That is how far the solar system really extends. And that is how far Gliese 710's gravitational influence will reach when it arrives. The timing of the encounter adds another dimension to the problem. Gliese 710 will reach closest approach in approximately 1.3 million years. In human terms, that is an unfathomable length of time. 1.3 million years ago, the species Homo erectus was the dominant hominin on Earth. Stone tools were the height of technology. Language, as we understand it, may not yet have existed. Everything that we call civilization, writing, agriculture, cities, science, all of it has occurred in the last 10,000 years. 1.3 million years is more than 100 times longer than all of recorded human history. It is so far in the future that predicting the state of human civilization at that time is not difficult. It is meaningless, and yet the physics does not wait for us to be ready. The gravitational interaction between Gliese 710 and the Oort cloud will proceed on its own schedule. The comets that are disturbed will begin their inward journeys, falling through the solar system on orbits that take hundreds of thousands of years to complete. The peak of the comet shower will not arrive until roughly 2 to 3 million years from now. And once it begins, it will persist for millions of years more, a slow-motion barrage of icy projectiles trickling into the inner solar system. Then something happened that changed everything. Not a new discovery about the star itself, but a new understanding of what its passage means. And this understanding did not come from a single study. It emerged gradually, across dozens of papers and simulations, as researchers began to calculate the full gravitational consequences of the encounter. What they found was not reassuring. In fact, what they found suggested that something is wrong with our assumptions about the safety of our cosmic neighborhood. The encounter with Gliese 710 would not be a minor perturbation. It would be the most significant disruption of the Oort cloud in millions of years. And we are, by any honest assessment, unprepared for what it might bring. Gliese 710 is not a spectacular star. It is not the kind of object that captures the public imagination or appears on the covers of popular science magazines. It is an orange dwarf, a K-type main sequence star, smaller and cooler than our Sun. Its surface temperature is roughly 4,300 Kelvin, compared to the Sun's 5,778 Kelvin. That temperature difference determines the star's colour. While our Sun appears yellow-white, Gliese 710 glows with a muted orange hue, the colour of cooling embers in a fireplace. It shines with only about a quarter of the Sun's luminosity. If you could swap it into the Sun's position, the Earth would receive far less light and heat. The oceans might freeze. The habitable zone, that narrow ring around a star where liquid water can exist on a planet's surface, would shrink dramatically inward to perhaps half or a third of Earth's current orbital distance. By almost every measure, it is a thoroughly ordinary star, one of billions of K-type dwarfs scattered throughout the Milky Way. Its mass is estimated at roughly 60% of the Sun's mass, or about 0.6 solar masses. In more tangible terms, that is approximately 2 nonillion kilograms, or 2 followed by 30 zeros. Its radius is correspondingly smaller, perhaps 60 to 70% of the Sun's radius, making it a somewhat more compact object. Despite being smaller and cooler, K-type stars like Gliese 710 have one notable advantage over stars like our Sun. They live longer, much longer. While the Sun has a total main sequence lifetime of roughly 10 billion years, a star with 60% of the Sun's mass can burn its hydrogen fuel for 40 billion years or more, far longer than the current age of the universe. Gliese 710 will still be shining long after the Sun has exhausted its fuel, expanded into a red giant, and collapsed into a white dwarf. It sits in the constellation Serpens Cauda, the tail of the serpent, and is currently visible only through a telescope with an apparent magnitude of about 9.7. The unaided human eye can see stars down to about magnitude 6 under ideal conditions. Gliese 710 is roughly 25 times fainter than that threshold. You could stand under the darkest sky on Earth, stare directly at its location, and see nothing. It is invisible to casual observation, hidden among the countless faint stars that populate the background sky. And yet this dim, unremarkable star has become one of the most intensely studied objects in modern astrometry. The science of measuring the positions and motions of stars. The story of its discovery as a threat begins not with Gliese 710 itself, but with the broader effort to catalogue stellar motions. Astronomers have long known that stars move. The ancient Greeks believed the stars were fixed to a crystalline sphere, eternal and unchanging. This belief persisted for nearly 2 millennia, but in 1718, the English astronomer Edmund Halley, the same Halley whose name adorns the famous comet, compared contemporary star catalogues with observations recorded by the ancient Greek astronomer Hipparchus nearly 2,000 years earlier. He found that 3 bright stars, Sirius, Arcturus, and Aldebaran, had shifted their positions by noticeable amounts. The stars were not fixed, they moved. These proper motions, as they came to be called, are typically tiny, measurable only in arcseconds per year. Even the fastest moving star visible to the naked eye, Arcturus, drifts by only about 2 arcseconds per year, an angle so small that it would take roughly 900 years for the star to move by the width of the full moon in the sky. But over millions of years, these motions accumulate. The constellations we see today are temporary patterns, snapshots of an ongoing stellar dance. In a million years, the Big Dipper will be distorted beyond recognition. Orion's belt will unravel. The sky of the far future will be as unfamiliar to us as an alien world. And among the millions of stars in slow, silent motion, some are moving toward us. The effort to identify approaching stars accelerated dramatically with the advent of space-based astrometry. Ground-based telescopes, even the best ones, are limited by the turbulence of Earth's atmosphere, which blurs stellar positions and limits the precision of proper motion measurements. But a telescope in space, above the atmosphere, can achieve measurements of extraordinary accuracy. The Hipparcos satellite, launched by the European Space Agency in 1989 and operational until 1993, was the first dedicated space astrometry mission. It measured the positions, parallaxes, and proper motions of approximately 118,000 stars with an accuracy of about 1 milliarcsecond. This was a revolutionary improvement over ground-based catalogues, and it opened the door to systematic studies of stellar encounters with the Sun. In 1999, Robert Matthews at Aston University in Birmingham, England, published an analysis that brought Gliese 710 into the spotlight. Using data from the Hipparcos satellite, Matthews was searching for stars whose 3-dimensional trajectories might bring them close to the Sun within the next few million years. He was not the first to attempt this. Astronomers had been studying stellar close approaches since at least the 1960s, when Joan Garcia Sanchez and collaborators at the Jet Propulsion Laboratory performed some of the earliest systematic searches. But the Hipparcos data, released in 1997, offered unprecedented positional accuracy for more than 100,000 stars, making it possible to trace stellar trajectories with much greater confidence than before. The method is conceptually simple but computationally demanding. For each star in the catalogue, you take the measured position, proper motion, parallax, and radial velocity, and you use these to calculate the star's three-dimensional position and velocity at the present time. Then you integrate the equations of motion forward in time, accounting for the gravitational field of the Milky Way, tracking where the star will be in 1 million, 5 million, 10 million years. You do the same for the Sun. And then you look for the point in time where the distance between the star and the Sun reaches its minimum. That minimum distance is the closest approach. Among the candidates Matthews identified, Gliese 710 stood out immediately. Based on the Hipparcos measurements, he estimated that the star would pass within about 1.1 light-years of the Sun, approximately 70,000 astronomical units, in roughly 1.4 million years. This was closer than any other star predicted to approach in the foreseeable future. It was closer than the current nearest stellar neighbour, Proxima Centauri, which sits at about 4.2 light-years. At 70,000 astronomical units, the star would graze the outer edge of the Oort Cloud, potentially disturbing some of the most loosely bound objects there. The astronomy community noted the result with genuine interest, but not with alarm, at least, not yet. 70,000 astronomical units placed the closest approach in the outermost, most diffuse region of the Oort Cloud, where the density of objects is lowest and the gravitational binding to the Sun is at its weakest. Some comets would be displaced, certainly. A modest increase in the long-period comet flux might follow, perhaps lasting a few 100,000 years, but the overall effect seemed manageable, well within the range of perturbations that the solar system has routinely experienced from passing stars over its 4.6 billion-year history. Gliese 710 was filed away as an interesting data point, a notable entry in the catalogue of stellar encounters, worthy of further study but not a cause for immediate concern. For nearly 2 decades, that assessment held. Papers were published, data was refined. New proper motion measurements from ground-based surveys nudged the predicted closest approach distance slightly in one direction or another. But the basic picture remained unchanged. Gliese 710 was a close encounter, but a manageable one. Then Gaia arrived, and the picture shattered. The Gaia spacecraft had been collecting data since 2014, and its successive data releases each brought improvements in precision that made the previous generation of measurements look almost crude by comparison. The second Gaia data release, published in April of 2018, contained astrometric measurements for more than 1.3 billion stars, along with radial velocities for roughly 7 million of the brightest ones. The radial velocity measurement is crucial. Proper motion tells you how a star is moving across the sky, left to right and up and down, but it tells you nothing about how fast the star is moving toward or away from you along the line of sight. That information comes from the radial velocity, measured by detecting the Doppler shift of the star's spectral lines. A star moving toward you has its light shifted slightly toward the blue end of the spectrum. A star moving away has its light shifted toward the red. For Gliese 710, the new Gaia radial velocity was measured at approximately negative 24 kilometers per second. The negative sign indicates motion toward us. Gliese 710 is blue shifted. It is falling toward the Sun at a speed of roughly 86,000 kilometers per hour. Combined with its sideways motion across the sky, this gives a total space velocity that points almost directly at the Oort cloud. The star is not just moving generally in our direction. It is aimed at us with a precision that, while purely coincidental, is nonetheless striking. When Philip Beski and Piotr Dybczynski at Adam Mickiewicz University in Poznan, Poland, incorporated the Gaia data into their trajectory calculations, the result was startling. The predicted closest approach distance shrank from 70,000 astronomical units to roughly 13,300 astronomical units. This was not a minor revision. It was a 5-fold reduction in the missed distance. And because gravitational force scales with the inverse square of distance, a 5-fold reduction in distance means a roughly 25-fold increase in the gravitational force at closest approach. The perturbation that Gliese 710 would exert on the Oort cloud was not slightly larger than previously estimated. It was dramatically, almost incomparably larger. Other research groups quickly confirmed the finding using the same Gaia data, and, in some cases, independent radial velocity measurements from ground-based spectrographs. Some used slightly different models of the Milky Way's gravitational potential, the combined gravitational field of all the matter in the galaxy, which affects the trajectories of both the Sun and Gliese 710 as they orbit the galactic center over millions of years. The galactic potential is not perfectly known. The distribution of dark matter in the galaxy, the mass of the central black hole, the structure of the spiral arms, all of these contribute to the potential and all carry uncertainties. These different models produced slightly different closest approach distances, ranging from about 10,000 to about 15,000 astronomical units. But the core finding was robust across every model tested. Gliese 710 would penetrate deep into the Oort Cloud, not the outermost fringe, not the transition zone, the interior, the region where the density of frozen objects is thought to be highest. To appreciate the physics of what happens during a stellar flyby, imagine the Oort Cloud as a vast swarm of tiny particles orbiting the Sun in slow, nearly circular paths at enormous distances. Each of these particles is held in place by the Sun's gravity, but the hold is tenuous. At 10,000 astronomical units, the Sun's gravitational acceleration is roughly 1/10 billionth of what it is at Earth's distance. These objects are not tightly bound. They are gently held, like dust motes floating in a still room. Now introduce a second gravitational source, Gliese 710, approaching from one direction. As the star draws near, it begins to exert its own gravitational pull on the Oort Cloud objects. The objects closest to the approaching star feel the strongest pull. Objects on the far side of the cloud, with the Sun between them and the visitor, feel a weaker pull. The Sun itself is also pulled toward the approaching star, but the Oort Cloud objects are pulled by slightly different amounts, depending on their positions. The result is a differential gravitational effect, what physicists call a tidal force. This tidal force stretches the cloud along the axis connecting the Sun and the approaching star, much as the Moon's gravity raises tides in Earth's oceans. The tidal force from a stellar flyby is not a simple push in one direction. It is a complex, three-dimensional perturbation that varies across the cloud and changes as the star moves along its trajectory. Objects on the near side are pulled away from the Sun. Objects on the far side are left behind as the Sun is pulled toward the star. Objects perpendicular to the approach axis are squeezed inward. The net effect is a reshuffling of orbits on a vast scale. This tidal force does different things to different objects depending on their location, their orbital velocity, and the timing of the encounter relative to their orbital phase. Objects that happen to be moving in roughly the same direction as the star's approach may receive an energy boost that pushes them onto more elongated orbits. Some of these elongated orbits will have perihelia, closest approach points to the Sun, that fall within the inner solar system. These are the objects that become comets. Others may receive enough energy to escape the solar system entirely, flung outward into interstellar space. Still others may be only slightly perturbed, their orbits tweaked by a fraction of a degree, settling into new configurations that may or may not bring them into the inner solar system at some later date. The simulations conducted by Dybczynski, Bersky, and others attempted to quantify these effects in detail. They populated model Oort clouds with millions of test particles, each one representing a frozen body at a specific distance and orbital configuration, distributed according to various theoretical density profiles. Some profiles concentrated mass in the inner Oort cloud between 2,000 and 20,000 astronomical units. Others spread it more evenly out to the full 100,000 astronomical unit radius. They then introduced Gliese 710 on its predicted trajectory, tracked the gravitational interactions over millions of simulated years, and recorded which particles were displaced, how their orbits changed, and how many were sent inward toward the Sun. The computational requirements were enormous. Each simulation required tracking millions of gravitational interactions over millions of time steps, but the results were consistent in their qualitative picture, even as they differed in quantitative detail. The encounter with Gliese 710 would produce a measurable, significant, and prolonged increase in the flux of long-period comets entering the inner solar system. And it gets worse. the increase would not be a brief spike, because Oort Cloud objects move so slowly, taking hundreds of thousands of years to fall from the outer solar system to the inner planets. The comets disturbed by the encounter would not all arrive at once. They would trickle in over a period of 1 to 2 million years or more after the star's closest approach. The shower would build gradually, like a slow tide rising, peak at some maximum intensity, and then slowly fade over subsequent millions of years. During this entire period, the inner solar system would contain significantly more long-period comets than it does today, and every additional comet is an additional opportunity for a collision with a planet. Not just Earth, Mars, Venus, even the gas giants could be struck. But Earth is the one that matters to us. Earth is the one where life exists. Earth is the one where fragile ecosystems and complex civilizations could be wiped away by a single well-placed impact. The probability of any single comet striking Earth is very small. A long-period comet entering the inner solar system has perhaps a 1 in a billion chance of hitting our planet on any given pass. That probability comes from the ratio of Earth's gravitational cross-section, which accounts for both its physical size and its gravity's ability to attract nearby objects, to the total area of the inner solar system through which the comet might travel. Earth is a tiny target in a vast arena, but these probabilities accumulate over time and over many comets. If the comet flux doubles for a period of 2 million years, and the average rate of long-period comets entering the inner solar system is currently about 1 per year, then during the shower, there would be roughly 2 per year. Over 2 million years, that is 4 million comets, passing through the inner solar system. With a 1 in a billion chance per pass, the expected number of Earth impacts over that period is roughly 4 in 1,000, or about 0.4%. That does not sound like much, but it is significantly higher than the background rate, and it applies to each 2 million year window of elevated activity. And if the comet flux increases by a factor of 4 rather than 2, which some models predict, the probability rises to roughly 1%. Still small in absolute terms. But consider what 1% means. It means that if you could replay this scenario 100 times in one of those 100 timelines, a major comet strikes Earth during the shower. 1% is the probability of rolling a specific number on a 100-sided die. It is not negligible, and it is not comforting, especially when you consider that a single impact from a comet larger than 10 kilometers in diameter could trigger a mass extinction event comparable to the one that ended the age of the dinosaurs. But here's the problem. These calculations depend on assumptions that are poorly constrained. We do not know the density profile of the Oort cloud. Is it densest in the inner region, between 2,000 and 20,000 astronomical units, and sparse beyond that? Or is it more evenly distributed? Different models of the Oort cloud's formation yield different density profiles, and we have no direct observations to distinguish between them. We do not know how many objects the cloud contains. Estimates range from 1 trillion to 100 trillion, a factor of 100 in uncertainty. We do not know the size distribution of those objects, how the number of bodies varies with their diameter. Are most of them small, sub-kilometer chunks? Or is there a significant population of larger bodies, 10 to 50 kilometers across, that could produce truly catastrophic impacts? We do not know the precise trajectory of Gliese 710, though we know it within a reasonably narrow range. The Gaia measurements are extraordinarily precise, but they are not perfect. The parallax carries an uncertainty of a few percent. The proper motion carries a similar uncertainty, and the radial velocity, while well measured, has an error bar that, when propagated forward over 1.3 million years, produces a range of possible closest approach distances spanning several thousand astronomical units. The most likely value is around 13,000 astronomical units. The 90% confidence interval extends from roughly 10,000 to perhaps 16,000 astronomical units. There is even a small but non-zero probability that the star could pass as close as 8,000 astronomical units. At that distance, the perturbation would be severe, and we do not know how the perturbation from Gliese 710 will interact with the ongoing perturbation from the galactic tide. These two effects are not independent. They can reinforce each other in complicated, non-linear ways, producing synergistic effects that neither would produce alone. The galactic tide operates continuously, slowly rotating the orbital planes of Oort Cloud objects over millions of years. It acts like a slowly turning dial, gradually moving objects from stable orientations to unstable ones. A stellar encounter then arrives and provides a sharp, impulsive kick. Objects that have been preconditioned by the galactic tide, their orbits already tilted toward instability, are far more likely to be dislodged by the encounter than objects that have not been preconditioned. Dybczynski has warned specifically about this synergy in multiple publications. In his models, the combined effect of the galactic tide and the Gliese 710 encounter produces a comet shower that is significantly more intense than what either mechanism would produce in isolation. The encounter is not just additive, it is multiplicative. The galactic tide sets the stage, and Gliese 710 delivers the blow. There is another complication that deserves attention. The mass of Gliese 710 is not precisely known. Stellar masses are among the most difficult quantities to measure in astronomy. For binary stars, masses can be determined from the orbital dynamics of the pair. But Gliese 710 is, as far as we know, a single star. Its mass is estimated from its luminosity, color, and spectral type, using models of stellar structure and evolution. These models are well tested and generally reliable, but they carry uncertainties of perhaps 10 to 15%. If Gliese 710's actual mass is at the upper end of the uncertainty range, say 0.7 solar masses instead of 0.6, the gravitational perturbation during the flyby would be correspondingly stronger. More troubling is the possibility that Gliese 710 has an unseen companion. Binary and multiple star systems are common in the galaxy. Roughly half of all Sun-like stars have at least one gravitationally bound companion. For smaller stars like Gliese 710, the binary fraction is lower, perhaps 30 to 40%, but it is far from negligible. If Gliese 710 has a companion, a faint red dwarf or a brown dwarf, orbiting at a distance of a few astronomical units, it would be very difficult to detect from Earth at a distance of 62 light-years. A brown dwarf companion in particular would emit so little light that it could easily hide within the glare of the primary star, invisible to all but the most sensitive instruments. Yet such a companion would increase the total mass of the system perhaps by 10 to 30%, and therefore increase the gravitational perturbation during the flyby by a corresponding amount. The effect would not be trivial. Even a modest increase in mass could shift the comet shower from a moderate enhancement to a severe one, pushing the impact probability upward. No companion has been confirmed through any observational method, but neither has one been definitively ruled out. High-resolution imaging techniques, such as adaptive optics and speckle interferometry, have searched for companions at angular separations consistent with a few tens of astronomical units at Gliese 710's distance, but these searches have not been comprehensive. Long-term radial velocity monitoring, which could detect the gravitational wobble induced by an orbiting companion, has been conducted, but the baseline of observations is not yet long enough to rule out companions on orbits longer than a few years. This remains an open question, and it is one that carries significant implications for the severity of the Oort Cloud perturbation. We may be underestimating the threat simply because we cannot see all of the incoming mass. The history of stellar encounters with our solar system provides additional context, and it is not entirely comforting. Gliese 710 is not the first star to have approached the Oort Cloud. Astronomers have used Gaia and Hipparcos data to identify numerous past encounters, tracing stellar trajectories backward in time. Most were distant and inconsequential, but one discovery in particular sent a chill through the field. In 2015, Eric Mamajek at the University of Rochester, along with Scott Barenfeld, Valentin Ivanov, and several other collaborators, announced that a small binary system called Schultz's star had passed through the outer Oort cloud approximately 70,000 years ago. The system consists of a faint red dwarf and an even fainter brown dwarf companion, orbiting each other in a tight pair. Together, the system has a total mass of only about 15% of the Sun's mass. It was discovered only in 2013 by Ralph Dieter Schultz, who noticed its relatively high proper motion in a survey of faint southern hemisphere stars. It had gone undetected for so long because it is extraordinarily dim, with an apparent magnitude of roughly 18, more than 100,000 times fainter than the faintest stars visible to the naked eye. Mamajek's analysis, based on a combination of proper motion and radial velocity measurements, showed that Scholz's star had passed the Sun at a closest approach distance of roughly 52,000 astronomical units, about 0.8 light-years. This placed it in the outermost, most tenuous region of the Oort Cloud. The passage occurred within the span of modern human existence. 70,000 years ago, anatomically modern humans were already living in Africa, the Middle East, and possibly early routes into Asia. Our ancestors were painting on cave walls, fashioning bone tools, and developing the rudiments of symbolic thought. The ice ages gripped the northern continents, and while they went about their lives utterly unaware, a small binary star was brushing past the frozen frontier of their solar system, its gravity reaching into the darkness to gently tug on the ancient icy bodies drifting there. Did any of those stirred comets eventually reach the inner solar system? It is possible, though extremely difficult to prove. The timescale for a disturbed Oort cloud object to fall inward is typically hundreds of thousands to millions of years. So any comets dislodged by Scholz's star 70,000 years ago are either still on their way, slowly spiraling inward through the vast emptiness between the Oort cloud and the planetary region, or they arrived recently enough that they have not yet been connected to the encounter. Some researchers have looked for excess comets with orbital properties consistent with a perturbation from the direction of Scholz's star's passage, but the results have been inconclusive. The effect was probably small, given the system's low mass and distant passage. But it was real. It happened. It happened while we were here. Gliese 710 will be different, profoundly different. Its mass is roughly 4 times that of the Scholz's star system. Its closest approach will be roughly 4 to 5 times closer. The gravitational perturbation will be on an entirely different scale. If Scholz's star was a gentle breeze rippling the surface of a pond, Gliese 710 will be a boulder thrown into the same pond. The ripples will be larger, deeper, and longer lasting. The wave of displaced comets will be bigger. The duration of the shower will be extended. And the probability of a significant impact event during the shower will be correspondingly higher. There is a way to quantify the relative severity of stellar encounters. Astronomers sometimes use a quantity called the impulse parameter, which combines the mass of the passing star with the inverse of the product of the closest approach distance and the relative velocity. A larger impulse parameter means a more disruptive encounter. When calculated for Gliese 710, the impulse parameter is roughly 10 to 50 times larger than the impulse parameter for Scholz's star, depending on the assumed velocity and closest approach distance. This places the Gliese 710 encounter in a category of its own among known recent and future stellar passages. And there is a temporal dimension to consider as well. The comets disturbed by Gliese 710 will not arrive in the inner solar system for 1 to 2 million years after the encounter, but the encounter itself is 1.3 million years in the future. That means the peak of the comet shower could arrive roughly 2.5 to 3.3 million years from now, and the shower could persist for millions of years beyond that. The effects of this single stellar passage will echo through the solar system for geological epochs. Multiple generations of species may evolve and go extinct within the duration of a single Gliese 710 comet shower. Meanwhile, we sit on Earth, aware of what is coming but unable to affect it. We can measure the star's position to within microarcseconds. We can calculate its trajectory to within a few thousand astronomical units. We can simulate the Oort cloud's response with millions of test particles on powerful computers. But we cannot move the star. We cannot redirect the comets before they are even dislodged. We cannot fortify the Oort cloud against gravitational intrusion. We are observers of a process that will unfold long after every person alive today is gone. Every language currently spoken is forgotten. Every building standing today has crumbled to dust and been buried beneath sedimentary layers. The physicist and writer Arthur C. Clarke once said that the dinosaurs went extinct because they did not have a space program. The implication was that a sufficiently advanced civilization could protect itself from cosmic threats. But the Gliese 710 scenario challenges even that optimistic framing. A space program might detect an incoming comet. It might even deflect one. But what about a shower of comets, hundreds or thousands of them, arriving over a period of millions of years? What kind of civilization could maintain vigilance for that long? What kind of infrastructure could sustain a planetary defense system across geological timescales? But here's what makes this truly terrifying. The geological record suggests that processes exactly like this one have shaped the history of life on Earth. Comet showers, impact events, mass extinctions. The pattern is there, embedded in the rocks, written in the fossils, visible in the layers of iridium and shocked quartz that mark the boundaries between geological eras. And Gliese 710 may be the next author of a new chapter in that ancient, brutal, beautiful story. The scientific community has approached the Gliese 710 problem from multiple angles, each one revealing a different facet of the threat and a different set of limitations in our understanding. 5 major lines of investigation have emerged over the past 2 decades, and each deserve careful examination. Let us walk through them, one by one, and see what each has revealed and where each has fallen short. The first approach is dynamical simulation, the most direct and mathematically rigorous method available. Researchers build a computer model of the outer solar system, populate the Oort Cloud with millions of test particles representing icy bodies at various distances and on various orbits, and then introduce Gliese 710 on its predicted trajectory. The simulation integrates the gravitational equations of motion forward in time, tracking every interaction between the star and each test particle, recording which objects are perturbed, how their orbits change, and crucially, how many are deflected inward onto trajectories that cross the inner solar system. The pioneering work in this area was done by Piotr Dybczynski and his collaborators at Adam Mickiewicz University, beginning in the early 2000s and continuing through the 2010s and into the 2020s. In their most detailed simulations, they modeled an Oort cloud containing 10 million test particles distributed according to various density profiles. Some models assumed a cloud that was densest in its inner regions, between 2,000 and 20,000 astronomical units. Others assumed a more uniform distribution. In each case, Gliese 710 was introduced on a trajectory consistent with the best available Gaia data, approaching the Sun at a speed of roughly 24 kilometers per second and passing at a closest approach of approximately 13,000 astronomical units. The results showed a clear and consistent pattern. The encounter produced a significant enhancement in the number of long-period comets entering the inner solar system. The enhancement was not instantaneous. Because Oort cloud objects travel slowly, taking hundreds of thousands of years to fall from the outer reaches to the vicinity of the Sun, the comet shower did not begin until roughly 500,000 to 1 million years after the star's closest approach. The shower then built gradually, reaching a peak roughly 1 to 2 million years after the encounter, before slowly declining over the next several million years. The numbers are striking. In some simulations, the comet flux during the peak of the shower increased by a factor of 2 to 4 above the background rate. In others, particularly those assuming a denser inner Oort cloud, the increase was even larger, reaching a factor of 5 or 6. Given that the current estimated rate of long-period comets, bright enough to be detected, entering the inner solar system is roughly 1 per year, a 4-fold increase would mean 4 such comets per year for a period of millions of years. Each one is a potential impactor. Each one carries kinetic energy measured in millions of megatons, and the total number of comets passing through the inner solar system during the shower could reach into the millions. But here's the problem with dynamical simulations. They are only as good as their inputs, and the inputs, as we have seen, are deeply uncertain. The density profile of the Oort cloud is unknown. The total number of objects is uncertain by 2 orders of magnitude. The velocity distribution of Oort cloud objects, which determines how they respond to gravitational perturbations, is poorly constrained by observation, and the precise trajectory of Gliese 710, while well measured by astronomical standards, still carries enough uncertainty to produce a wide range of outcomes when projected over 1.3 million years. Different reasonable assumptions about these inputs can produce simulated comet showers that differ by an order of magnitude in intensity. Some models predict a gentle drizzle of additional comets, barely noticeable above the background rate. Others predict a torrent that could transform the inner solar system into a shooting gallery for millions of years. The simulations also face a fundamental computational limitation. Modeling every gravitational interaction among billions of Oort Cloud objects is currently impossible. Even 10 million test particles is a tiny fraction of the estimated 1 trillion to 100 trillion objects in the real Oort Cloud. Researchers must use statistical extrapolation to scale their results upward, and these extrapolations carry their own uncertainties. The qualitative conclusions are robust. The encounter will produce a comet shower, but the quantitative details remain frustratingly imprecise. There is another subtlety that makes the simulations even more challenging. The Oort Cloud does not exist in gravitational isolation. It is constantly being sculpted by the galactic tide, that gentle but persistent gravitational gradient produced by the combined mass of the entire Milky Way. The tide preferentially affects objects on orbits oriented in certain directions relative to the galactic plane, slowly rotating their orbital planes and changing their perihelion distances over millions of years. When Gliese 710 arrives, its gravitational perturbation will not act on a static population of comets. It will act on a population that has already been extensively shaped and reshaped by the galactic tide. The two effects can reinforce each other or partially cancel, depending on the specific geometry of each comet's orbit relative to the star's trajectory and the galactic plane. Capturing this interplay accurately requires modeling both perturbations simultaneously over millions of years, which demands enormous computational resources and introduces additional sources of uncertainty related to the galactic gravitational potential itself, which is not known to perfect precision. Furthermore, the simulations must account for the fact that comets perturbed from the Oort Cloud do not travel in straight lines to the inner solar system. They follow elongated elliptical or hyperbolic orbits, and along the way they are subject to the gravitational influence of the giant planets, particularly Jupiter and Saturn. A comet that has been nudged inward by Gliese 710 might be captured into a shorter period orbit by Jupiter, or it might be ejected entirely from the solar system by a close planetary encounter. The giant planets act as both shields and randomizers, deflecting some comets away from Earth while redirecting others onto more dangerous trajectories. This planetary filtering effect must be modeled explicitly, adding yet another layer of complexity and uncertainty to the calculations. The second approach involves looking for evidence of past comet showers preserved in the geological record. If stellar encounters have triggered comet showers in the past, and if those showers produced impacts on Earth, then the evidence should be there, embedded in the rocks. Impact craters, layers of iridium, a rare element that is abundant in asteroids and comets, but scarce in Earth's crust. Shocked quartz, a form of silicon dioxide that can only be produced by extreme pressure, such as that generated by a hypervelocity impact. Tektites, glassy droplets of melted rock ejected from impact sites and scattered across wide areas. These are the signatures of cosmic bombardment, and geologists have been cataloguing them for decades. In the 1980s, two landmark studies ignited a fierce debate that continues to this day. The first was by David Raup and Jack Sepkoski at the University of Chicago, who analyzed the timing of mass extinction events over the past 250 million years and claimed to find a periodic pattern with extinctions occurring at roughly 26 million year intervals. The second was by Walter Alvarez and Richard Muller at the University of California, Berkeley, who performed a similar analysis on the ages of large impact craters and found a similar periodicity. If real, this periodicity would suggest that some external, cyclical mechanism was periodically bombarding Earth with impactors, producing mass extinctions at regular intervals. The proposed explanations were dramatic. One was the nemesis hypothesis suggested by Muller and his colleagues. It posited that the Sun has an unseen companion star, a faint red dwarf or brown dwarf, on a highly elliptical orbit with a period of roughly 26 million years. At each perihelion passage, this hypothetical companion would plunge through the Oort Cloud, triggering a massive comet shower that lasted for 1 million years or so before subsiding. The timing matched the proposed extinction periodicity. The mechanism was physically plausible. There was only one problem. Despite decades of searching, no such companion has ever been found. Wide-field infrared surveys, including those conducted by the Wide Field Infrared Survey Explorer, known as WISE, launched in 2009, have scanned the entire sky at infrared wavelengths sensitive to the faint heat emission of brown dwarfs and cool red dwarfs. These surveys have ruled out the existence of any object with a mass greater than a few Jupiter masses within about 26,000 astronomical units of the Sun. The Nemesis hypothesis is now considered effectively dead. If the Sun had a companion massive enough to perturb the Oort cloud significantly, we would have found it by now. A related hypothesis, proposed by Michael Rampino and others, suggested that the periodicity might be driven not by a companion star, but by the Sun's oscillation through the galactic plane. As the Sun bobs up and down through the dense midplane of the Milky Way, the galactic tidal force on the Oort cloud varies in a roughly periodic way. Rampino argued that the timing of galactic plane crossings correlated with the timing of major extinction events, suggesting a causal connection. Each time the Sun passed through the densest part of the galactic disk, the enhanced tidal force would stir the Oort cloud, producing a comet shower that arrived at Earth 1 to 2 million years later. But the statistical evidence for the claimed periodicity remains contested. Some analyses find a significant periodic signal in the extinction data, others do not. The fundamental problem is that the sample size is small. There are only about 5 major mass extinctions in the past 500 million years, and perhaps a dozen to 20 lesser extinction events. The dating of these events, while increasingly precise thanks to radiometric methods, still carries uncertainties of a few 100,000 to a few million years. When the sample is small and the uncertainties are large, it becomes very easy to see patterns that are not there. The debate has continued for over 40 years without resolution, and it may never be fully resolved with the data currently available. What the geological record does show clearly, beyond any doubt, is that large impacts happen and they can be catastrophic. The Earth bears the scars of these events, though time and tectonic activity have erased many of them. There are roughly 190 to 200 confirmed impact craters on Earth, ranging in size from a few tens of meters to hundreds of kilometers across. But this catalogue is profoundly incomplete. Earth's surface is constantly being recycled by plate tectonics, which subducts oceanic crust into the mantle and reshapes continents over hundreds of millions of years. Approximately 60% of Earth's surface is oceanic crust, all of which is younger than about 200 million years. Any craters that formed on ocean floors before that time have been destroyed. Even on continental crust, erosion, sedimentation, volcanic activity, and tectonic deformation conspire to obscure or obliterate impact structures over geological time. The current catalogue of known craters, therefore, represents only a fraction of the impacts Earth has actually experienced. The largest confirmed crater is the Vredefort structure in South Africa, roughly 300 kilometers in diameter, formed about 2 billion years ago. The Sudbury Basin in Ontario, Canada, roughly 250 kilometers across, is about 1.85 billion years old. These ancient structures have been so heavily eroded and deformed that they are barely recognizable as impact features. Only detailed geological analysis, looking for shocked minerals, elevated iridium concentrations, and distinctive structural deformation, reveals their violent origins. More recent craters tend to be better preserved. The Popigai crater in Siberia, roughly 100 kilometers across and about 35 million years old, still retains much of its original structure. The Chesapeake Bay impact structure, roughly 85 kilometers in diameter, and also about 35 million years old, lies partially buried beneath the sediments of the modern bay, discovered only through drilling and geophysical surveys in the 1990s. But the most famous impact event in Earth's history, and the one most relevant to the Gliese 710 scenario, is the Chicxulub impact. The Chicxulub impactor struck the Yucatan Peninsula 66 million years ago and ended the age of the dinosaurs. The impact was roughly 10 to 15 kilometers in diameter. It struck the Earth at a velocity of approximately 20 kilometers per second. The energy released was equivalent to roughly 10 billion Hiroshima-sized nuclear detonations, or about 100 million megatons of TNT. To put that in context, the largest nuclear weapon ever detonated, the Soviet Tsar bomber in 1961, yielded about 50 megatons. The Chicxulub impact released roughly 2 million times more energy. The impact generated a crater roughly 180 kilometers in diameter and perhaps 30 to 40 kilometers deep in the initial moments, though the crater rapidly collapsed and was partially filled by rebounding rock and debris. The impact triggered a cascade of global catastrophes. Enormous quantities of rock and dust were ejected into the atmosphere and into ballistic trajectories that carried them around the globe. As this ejector re-entered the atmosphere, it heated the air to extreme temperatures, igniting wildfires across vast areas of the planet. The fires may have consumed a significant fraction of Earth's forests and grasslands. Soot and dust in the atmosphere blocked sunlight for months to years, plunging the planet into an impact winter in which photosynthesis largely ceased. Sulfur-bearing minerals in the rocks of the Yucatan were vaporized by the impact, producing sulfuric acid aerosols that fell as acid rain, devastating freshwater and shallow marine ecosystems. The combined effect was the collapse of food chains worldwide, from the oceanic plankton that formed the base of marine food webs to the large herbivorous dinosaurs on land. Roughly 75% of all species on Earth went extinct. While the Chicxulub impactor is generally thought to have been an asteroid, likely a carbonaceous chondrite based on its chemical signature, comets are fully capable of producing similar or even greater devastation. In fact, because long-period comets typically travel faster than asteroids when they reach the inner solar system, often at velocities of 40 to 60 kilometers per second compared to 15 to 25 for asteroids, a cometary impact of the same size would release even more kinetic energy. A 10-kilometer comet arriving at 50 kilometers per second would release roughly 6 times the energy of the Chicxulub impact. The consequences would be proportionally worse. The third approach to understanding the Gliese 710 problem focuses on the broader context of stellar encounters. Rather than studying Gliese 710 in isolation, some researchers have attempted to characterize the full history and future of stellar close approaches to the Sun using the Gaia catalogue as their primary tool. Corinne Baylor-Jones at the Max Planck Institute for Astronomy in Heidelberg, Germany, has been a leading figure in this effort. Using successive Gaia data releases, he and his collaborators have identified hundreds of stars that have passed or will pass within 2 parsecs, approximately 6.5 light-years, of the Sun over a timespan of plus or minus 10 million years from the present. For each encounter, they calculated the closest approach distance, the relative velocity at closest approach, the mass of the passing star where it could be estimated, and the resulting gravitational perturbation parameter. The results paint a picture of a solar system that is far less isolated than we typically imagine. Over any 10 million year window, dozens of stars pass close enough to exert at least some influence on the outer Oort cloud. Most of these encounters are minor, producing perturbations too weak to significantly alter the cometary flux in the inner solar system. But every few million years, on average, a star passes close enough to produce a detectable enhancement in the comet rate. And every few tens of millions of years, a star may pass close enough to produce a significant comet shower. Gliese 710 is simply the next in this long series of encounters, but it is predicted to be unusually close. In fact, based on current data, it will be the closest stellar encounter in the next 10 million years. No other known star comes as close. Baylor-Jones has also highlighted an important and troubling caveat. The Gaia catalogue, despite its extraordinary scope, is not complete. It has limitations. Very faint stars, particularly the smallest red dwarfs, with masses below about 10% of the Sun's mass, may be too dim for Gaia to have measured reliably, especially if they are located more than a few dozen light-years away. Brown dwarfs, substellar objects with masses below about 8% of the Sun's mass, are even harder to detect. These objects emit almost no visible light. They glow faintly in the infrared, but Gaia is an optical telescope. It is essentially blind to brown dwarfs beyond a few parsecs. This matters because low-mass stars and brown dwarfs are by far the most common objects in the galaxy. Population estimates suggest there may be as many brown dwarfs as there are stars. If this is true, then for every stellar encounter that Gaia has identified, there may be one or more unseen encounters by faint, low-mass objects that slipped through the catalogue entirely. Most of these invisible encounters would involve objects too small to produce significant perturbations. But occasionally, a relatively massive brown dwarf, perhaps 40 to 70 times the mass of Jupiter, could pass through or near the Oort Cloud without anyone knowing. The perturbation from such an encounter would be modest compared to Gliese 710, but it would not be zero, and because these encounters are invisible, their cumulative effect on the Oort Cloud's structure and the long-period comet flux is essentially unknown. We are working with an incomplete census, and the missing entries are precisely the ones that are hardest to detect. There is also the question of stellar multiplicity. Many stars travel with companions, forming binary or even triple systems. When a binary star passes near the Sun, the perturbation can be significantly larger than what the primary star alone would produce, because the companion adds mass and creates a more complex and extended gravitational field. In some cases, the companion may actually pass closer to the Sun than the primary, depending on the geometry of the binary orbit. Gaia can detect many binary systems, but closely separated pairs may appear as single sources, and the companion's contribution to the perturbation would be underestimated. Gliese 710 itself has been scrutinized for possible companions. So far, no companion has been definitively detected, but the possibility cannot be entirely excluded, particularly for a faint companion in a wide orbit that would be difficult to resolve at the star's current distance. This means that there could be approaching stars, or even substellar objects, that are not in the Gaia catalogue. The most threatening future encounter might not be Gliese 710. It might be a faint red dwarf or a rogue brown dwarf that we have not yet detected, barreling toward the solar system on a trajectory that will carry it even deeper into the Oort Cloud. We are tracking the threats we can see, but there may be threats we cannot. The fourth approach tackles the problem from the perspective of planetary defense. Even if we accept that Gliese 710 will eventually send a shower of comets into the inner solar system, the question remains, can we do anything about it? Can we detect incoming comets early enough to deflect or destroy them before they reach Earth? The honest answer at present is no. Our current planetary defense capabilities are focused almost entirely on near-Earth asteroids, objects in the inner solar system whose orbits bring them within 1.3 astronomical units of the Sun and potentially within striking distance of Earth. Programs like NASA's Center for Near-Earth Object Studies and the forthcoming NEO Surveyor Space Telescope, scheduled for launch in the mid-2020s, are designed to find and catalogue these asteroids, track their orbits, and assess impact probabilities. They are not designed to detect long-period comets. The reason is fundamentally practical. Near-Earth asteroids move on relatively predictable orbits within the inner solar system. They can be observed repeatedly over months and years, allowing their orbits to be determined with high precision. If a threatening asteroid is identified, there may be decades or even centuries of warning before a potential impact. This gives us time to plan and execute a deflection mission. NASA's DART mission, which successfully altered the orbit of the small asteroid Dimorphos in September of 2022, demonstrated that kinetic impact deflection is technically feasible. A spacecraft can be sent to collide with an asteroid at high speed, transferring momentum and nudging the asteroid's orbit enough to prevent a collision with Earth. But long-period comets are a fundamentally different problem, and the differences are not just quantitative. They are qualitative. A long-period comet approaches from the outer solar system on an extremely elongated orbit. It has never been near the Sun before, or at least not within recorded history. It is invisible until it gets close enough for sunlight to warm its icy surface and produce the coma and tail that make comets detectable. Depending on its size and composition, it might not become visible until it is within 5 to 10 astronomical units of the Sun, roughly the distance of Jupiter. At that point, with a typical inbound velocity of 40 to 50 kilometers per second, it may be only 1 to 2 years from reaching Earth's orbit. 1 to 2 years. That is not enough time to design, build, launch, and navigate a deflection mission. The DART mission, from conception to impact, took roughly 7 years. Even an expedited response, using a pre-existing spacecraft design, would require at least 3 to 4 years. And that assumes the comet is detected early and its orbit is precisely determined, which is far from guaranteed. Comets are physically different from asteroids. They are made of volatile ices mixed with rock and dust. When heated by the sun, they outgas violently, producing jets of gas and debris that can alter their trajectories in unpredictable ways. This non-gravitational acceleration makes their orbits harder to compute. A comet that appears headed for a comfortable miss might veer closer to Earth due to outgassing. We might not know the true trajectory until dangerously late. Furthermore, comets are structurally weaker than most asteroids. They are often described as dirty snowballs or, more accurately, icy dirt balls with low bulk densities and porous, fragile structures. A kinetic impactor that would successfully deflect a solid rocky asteroid might simply shatter a comet, producing a debris cloud that spreads along the original trajectory. Instead of one large impactor, you could end up with hundreds of smaller impactors, each still capable of causing significant damage. This is sometimes called the shotgun problem, and it has no easy solution. The DART mission proved we can hit an asteroid and change its orbit, but DART targeted a small, well-characterized asteroid in a well-known orbit, with years of advanced planning and precise trajectory data. Applying the same approach to a long-period comet detected with perhaps 18 months of warning, traveling at twice the speed on an uncertain trajectory, composed of fragile ices that may fragment upon impact, is a vastly more difficult challenge. It is not clear that any technology currently in development, or even in the conceptual stage, could reliably deflect such an object. We are, for the moment, defenseless against long-period cometary threats. Some theorists have proposed alternatives to kinetic impactors for cometary defense. Nuclear standoff detonation, in which a nuclear device is detonated near the surface of an approaching comet to vaporize a layer of material and push the comet off course through the resulting blast of gas, is perhaps the most discussed. The idea has a certain brute force elegance. Nuclear weapons are the most powerful energy sources humanity can deploy in space, and the standoff approach avoids the fragmentation problem because the weapon does not physically strike the comet. Instead, it bathes one hemisphere in intense radiation, causing the surface material to flash vaporize and eject outward like a rocket exhaust, pushing the remaining mass in the opposite direction. But even this approach faces severe practical obstacles when applied to long-period comets. The weapon must be launched, navigated across millions of kilometers of space, and detonated at precisely the right distance and orientation relative to a small, dark, poorly characterized target that may be tumbling unpredictably. The comet's internal structure, whether it is a monolithic block or a loosely bound rubble pile, determines how it responds to the blast, and we generally do not know this until we get close enough to study it, which may be far too late for a deflection attempt. There is also the political dimension. International treaties currently restrict the deployment of nuclear weapons in space, and amending those treaties in the short window between comet discovery and potential impact would require extraordinary diplomatic speed. The uncomfortable conclusion is that our planetary defense capabilities, while rapidly improving for the near-Earth asteroid threat, have a significant blind spot when it comes to long-period comets. This blind spot is not primarily technological, it is architectural. Our detection systems are designed to find objects in the inner solar system. Our deflection concepts assume years of advance warning. Long-period comets violate both assumptions. Closing this gap would require a fundamentally different approach. Deep space surveillance telescopes, stationed far from the Sun, capable of detecting faint objects at great distances in the infrared, combined with pre-positioned deflection assets that could be deployed on short notice. Such a system is technologically conceivable but would require decades of development and enormous investment. As of now, no space agency has such a program on its roadmap. The fifth and final approach is perhaps the most speculative, but also the most profound in its implications. It asks whether the Gliese 710 encounter, and encounters like it throughout solar system history, have played a direct role in shaping the evolution of life on Earth. This is the intersection of stellar dynamics and evolutionary biology, a field sometimes called astrobiology, or more narrowly, impact biology, and it connects the motions of stars to the fates of species in ways that are both elegant and deeply unsettling. The idea is conceptually straightforward. If stellar encounters periodically perturb the Oort cloud and send comet showers into the inner solar system, and if those comet showers occasionally produce major impacts on Earth, then the history of life on this planet is partly written by the stars. The timing of mass extinctions, the pace of evolutionary change, the rise and fall of entire lineages of organisms, all of these might be influenced by the gravitational choreography of stars passing through the solar neighborhood. Evolution, in this view, is not a purely biological process driven solely by mutation, natural selection, and environmental change on Earth's surface. It is a cosmic process, punctuated by catastrophic events, whose timing is set by the motions of objects tens of light years away. Michael Rampino, a professor of biology and environmental studies at New York University, has been one of the most persistent and articulate advocates of this idea. In a series of papers spanning from the 1980s to the 2020s, he has argued that the roughly 26 to 30 million year periodicity in mass extinctions, if real, can be most naturally explained by the Sun's oscillation through the galactic plane. As the Sun bobs above and below the dense midplane of the Milky Way, the tidal force on the Oort cloud varies in a quasi-periodic way. When the Sun passes through the midplane, the tidal force is strongest and the comet flux increases. Rampino has pointed to correlations between the timing of galactic plane crossings and the timing of major extinction events, as well as the timing of large impact craters, arguing that the match is statistically significant and physically plausible. Others have challenged this interpretation vigorously. The statistical methods used to identify periodicity have been questioned. The dating of extinction events and impact craters has been debated. Alternative explanations for mass extinctions, including volcanic eruptions such as the massive flood basalt events associated with several major extinctions, climate change, ocean chemistry shifts, and evolutionary dynamics, have been proposed and defended. The Deccan Traps in India, for example, represent one of the largest volcanic events in Earth's history, erupting roughly at the same time as the Chicxulub impact 66 million years ago. Some researchers argue that the Deccan eruptions, not the impact, were the primary driver of the end Cretaceous extinction, or at least a major contributor. The Siberian Traps, which erupted roughly 252 million years ago, coincide with the even more devastating Permian-Triassic extinction, the worst mass extinction in Earth's history, which killed roughly 96% of all marine species and 70% of terrestrial vertebrate species. No impact crater of the right age has been convincingly linked to the Permian-Triassic event, suggesting that volcanism alone can cause mass extinctions without any cosmic trigger. This significantly weakens the case for a purely impact-driven periodicity in the extinction record. The debate is far from settled, and it may never be fully resolved with current data. The fossil record is incomplete, the crater record is fragmentary, and the statistical methods used to detect periodicity in sparse, noisy datasets are inherently prone to false positives. The 26 million year signal may be real, or it may be a statistical artifact. Distinguishing between these possibilities may require not more sophisticated analysis of existing data, but fundamentally new data sources altogether. Yet the possibility remains alive, and it takes on a new dimension when we consider Gliese 710. If past stellar encounters have indeed contributed to comet showers that produced mass extinctions, then the approaching encounter is not just an astronomical curiosity. It is a potential future agent of biological transformation. The comet shower it produces, may be the trigger for the next major extinction event on Earth. Not in the near future when the star passes, but in the deeper future when the perturbed comets arrive. The timeline is staggering in its elongation. The star arrives in 1.3 million years. The comet shower peaks 1 to 2 million years later. The biological consequences may not be fully apparent until millions of years after that, as ecosystems collapse, recover, and eventually give rise to entirely new assemblages of species that fill the ecological niches left vacant by the extinct. From the moment the first comet is dislodged from the Oort Cloud to the moment the last evolutionary aftershock ripples through the biosphere, the causal chain set in motion by Gliese 710's passage could span 5 to 10 million years. A single gravitational whisper echoing across geological time. Each of these 5 approaches has revealed an important piece of the puzzle. Dynamical simulations demonstrate that the encounter will produce a significant perturbation of the Oort cloud. The geological record shows that past perturbations have had devastating consequences for life on Earth. The Census of Stellar Encounters confirms that Gliese 710 represents the closest known future approach by a substantial margin. Planetary defense analysis reveals a stark truth. We are essentially unprepared for long-period cometary threats, and the astrobiological perspective raises the haunting possibility that the pattern of life and death on Earth is linked, in ways we are only beginning to appreciate, to the gravitational dynamics of nearby stars. But none of these approaches provides a complete or definitive answer. Each is limited by uncertainty, by incomplete data, by the sheer difficulty of predicting events that will unfold over timescales of millions of years. We are left with a picture that is clear in its broad outlines, but blurred in its details. Something significant is approaching. We know approximately when it will arrive. We know approximately where it will pass, but we do not know, with any confidence, how bad the consequences will be. And we are almost certainly unable to prevent them. And this is where the answer becomes deeply unsettling. There is a deeper truth embedded in the story of Gliese 710, and it goes beyond the specific details of trajectories and comet showers and impact probabilities. It is a truth about the nature of the solar system itself, about its relationship to the galaxy it inhabits, and about the fundamental fragility of the conditions that have allowed complex life to flourish on Earth for the past 500 million years. We tend to think of the solar system as a self-contained entity, 8 planets orbiting a star, held together by gravity, moving through space as a complete and isolated unit. The textbook diagrams reinforce this impression. They show the Sun at the center, the planets arranged in neat concentric orbits, and nothing beyond. The solar system, in this familiar picture, has clear boundaries and no meaningful external influences. What happens within remains within. What happens outside stays outside. The Oort cloud shatters this illusion entirely. It reveals the solar system not as a fortress but as an open system, one whose outermost reaches are in constant dialogue with the galaxy. The boundary between what belongs to the Sun and what belongs to interstellar space is not a wall. It is a gradient, a diffuse transition zone where the Sun's gravity fades to nearly nothing, and the gravitational influence of the galaxy as a whole becomes dominant. Objects in the outer Oort cloud are bound to the Sun only in the most tenuous and conditional sense. They orbit the Sun, technically, but their orbits are so vast and so slow that even the gentlest external perturbation can reshape them dramatically. This means the solar system is permeable. It is open to influence from outside. Stars passing through the solar neighborhood, the gravitational tide of the Milky Way, the occasional close encounter with a giant molecular cloud, all of these external forces reach into the solar system through the Oort cloud, stirring its contents and occasionally sending icy bodies plunging inward toward the planets. The inner solar system, where we live, where the rocky planets orbit and life exists, is not insulated from these external perturbations. It simply experiences them indirectly through the intermediary of the Oort cloud, and on timescales so long that we rarely notice. Gliese 710 makes this permeability vivid and concrete. Here is a specific star with a known mass and a measured trajectory that will reach into the solar system and rearrange its contents, not metaphorically, physically, gravitationally. It will change the orbits of billions of icy bodies, redirect them onto new paths, and send some of them cascading inward toward the inner solar system over the following millions of years. The encounter is not hypothetical. It is not a thought experiment. It is a measured prediction based on the best astronomical data we have, and it will happen. But Gliese 710 is not special in kind. It is only special in proximity and timing. The galaxy has been doing this to the solar system for 4.5 billion years. Every few million years, a star passes close enough to stir the Oort Cloud. Every few tens of millions of years, a particularly close or massive encounter triggers a significant comet shower. And every few 100 million years, by chance, one of those comets strikes Earth with enough energy to cause a mass extinction. This is not a flaw in the solar system's design. It is the solar system's design. The Oort Cloud is not a passive reservoir that occasionally malfunctions. It is a dynamic interface between the Sun's gravitational domain and the galaxy's gravitational environment, and cometary influx is one of its natural outputs. This realization changes how we think about the stability of the solar system, and, by extension, the stability of Earth's biosphere. We know that the inner solar system is dynamically stable over timescales of billions of years. The planetary orbits are, to a good approximation, predictable and unchanging. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. They will continue to orbit the Sun in roughly their current configurations for the foreseeable future. But this dynamical stability is not the same as environmental stability for any individual planet. The inner solar system may be stable in its orbital mechanics, but it is vulnerable to bombardment from its own periphery. Think of it this way. The solar system is like a house built on solid foundations. The walls do not move, the roof does not leak, the structure is sound. But the house is located in a neighborhood where, every few million years, someone throws a rock through the window. The rock does not come from inside the house. It comes from outside, launched by a neighbor who happens to walk past at the wrong distance with the wrong mass. The house survives. But anything fragile inside, a vase, a window, an ecosystem with 75% of its species might not. This analogy extends further. The neighborhood itself is not malicious. The neighbors are not aiming at the house. They are simply going about their business, following their own gravitational orbits through the galaxy. The rocks are not deliberately launched. They are accidentally dislodged from the rubble pile in the yard, the Oort Cloud, by the gravitational tug of a passerby. The whole process is mechanical, impersonal, and inevitable. Given enough time and enough passers-by, rocks will be thrown and windows will be broken. It is as a statistical certainty. The question then becomes, how often and how bad? And here the Gliese 710 encounter provides a useful calibration point. We know, from the work of Baylor Jones and others, that stellar encounters of various intensities occur with a roughly predictable frequency. We know that the Oort Cloud responds to these encounters in ways that can be modelled, at least approximately. And we know from the geological and paleontological record that large impacts have occurred on Earth throughout its history, with consequences ranging from regional devastation to global mass extinction. Putting these threads together, we can begin to construct a probabilistic picture of Earth's bombardment environment over geological time. The picture is not precise. The uncertainties are enormous, spanning orders of magnitude in some parameters, but its broad features are becoming clearer with each new data release from Gaia and each new analysis of the geological record. The background rate of long-period comets entering the inner solar system is roughly one detectable comet per year. Most of these comets pass through without incident, crossing Earth's orbit at a safe distance. The probability of any individual long-period comet actually striking Earth is extremely small, roughly 1 in a billion per orbit crossing. But over millions of years, the numbers add up. If a comet shower increases the influx by a factor of 4 for a period of 2 million years, that means roughly 8 million long-period comets passing through the inner solar system during the shower. The probability of at least one impact during the shower rises to roughly 1%. Small but not negligible, and over billions of years, with dozens of significant comet showers triggered by stellar encounters, the cumulative probability of at least one major cometary impact becomes very high, essentially certain in fact. What makes this calculation particularly sobering is the energy involved. We tend to think of asteroid impacts as the primary cosmic threat, and with good reason. Near-Earth asteroids are more numerous, better characterized, and more immediately dangerous than long-period comets. But when a long-period comet does strike, the consequences can be disproportionately severe. The reason is velocity. An asteroid in a near-Earth orbit might strike at 15 to 25 kilometers per second. A long-period comet, falling from the outer solar system on a nearly parabolic orbit, can arrive at 40 to 70 kilometers per second. Because kinetic energy scales as the square of velocity, a comet traveling at 50 kilometers per second carries roughly 4 to 9 times the kinetic energy of an asteroid of the same mass traveling at 20 kilometers per second. A 5-kilometer comet arriving at 55 kilometers per second would release approximately the same energy as a 10-kilometer asteroid arriving at 20 kilometers per second. The comet is half the size but carries the same punch. Moreover, comets are chemically distinct from most asteroids. They carry enormous quantities of volatile compounds, water ice, carbon dioxide, methane, ammonia, and a rich variety of organic molecules. When these volatiles are flash vaporized by the heat of atmospheric entry and impact, they inject enormous quantities of water vapor, carbon dioxide, and other gases into the atmosphere. The water vapor acts as a potent greenhouse gas in the short term, but also contributes to stratospheric chemistry that can destroy ozone. The carbon dioxide contributes to long-term warming after the initial impact winter subsides. The sulfur compounds, if the comet strikes sulfur-bearing rock as the Chicxulub impactor did, produce sulfuric acid aerosols that cause acid rain and cooling. The net effect on climate depends on the specific composition of the comet and the geology of the impact site. But in every scenario, the environmental disruption is severe and global. This is the deeper truth that Gliese 710 reveals. Mass extinctions caused by cometary impacts are not freak accidents. They are not anomalous events that happen once and never again. They are a predictable, recurring feature of the solar system's interaction with its galactic environment. The Chicxulub impact was not a cosmic fluke. It was an almost inevitable consequence of the solar system's 4.5 billion-year journey through a galaxy full of passing stars, each one capable of stirring the Oort Cloud and sending fresh comets sunward. This has profound implications for how we think about the long-term future of life on Earth and about the prospects for complex life elsewhere in the galaxy. If cometary bombardment is a recurring and essentially unavoidable feature of planetary systems embedded in stellar environments, then every planet in the galaxy that hosts complex life faces the same threat. Every star has its own Oort Cloud analog, or at least the potential for one. Every star moves through a galaxy full of other stars. Encounters are inevitable. Perturbations are inevitable. Cometary influx is inevitable. And occasionally, catastrophic impacts are inevitable. The implications for the search for extraterrestrial intelligence are particularly interesting. The galactic habitable zone, that annular region of the Milky Way where conditions are thought to be most favorable for life, is typically defined by metallicity and radiation levels. Stars need enough heavy elements to form rocky planets, and they need to be far enough from the galactic center to avoid intense radiation from supernovae and active galactic nuclei. But the stellar encounter rate varies across the galaxy too. In dense stellar environments, particularly in globular clusters and near the galactic center where stars are packed more tightly together, close encounters are far more frequent. The Oort cloud of a star in a dense cluster would be stripped away entirely within a few 100 million years, repeatedly perturbed by passing neighbors until nothing remains. Such a star might be safer from cometary bombardment, but it would also lack the reservoir of volatile-rich material that may have delivered water and organic compounds to the inner planets during the solar system's early history. The relationship between stellar density, cometary bombardment, and the emergence of complex life is more nuanced than it might first appear, and it adds another dimension to the already complex question of where in the galaxy life might flourish. This might seem like a reason for despair. If the galaxy is essentially a machine that periodically resets the biosphere of every habitable planet, What chance does any civilization have of surviving in the long term? But there is another way to look at it, and it is not entirely pessimistic. Mass extinctions, for all their horror, are also engines of evolutionary innovation. The Chicxulub impact ended the age of the dinosaurs, but it also created the ecological opportunity for the rise of mammals. Without that catastrophe, the lineage that eventually produced primates, and then hominids, and then modern humans, might never have diversified into the niches that dinosaurs had occupied for over 150 million years. Every mass extinction in the fossil record is followed by an adaptive radiation, a burst of evolutionary creativity in which surviving lineages diversify rapidly to fill the ecological vacancies left by the extinct. The Ordovician extinction gave way to the diversification of fishes. The Permian extinction gave way to the rise of the dinosaurs and the first mammals. The Cretaceous extinction gave way to the age of mammals and eventually to human civilization. The pattern is striking in its consistency. Before the end Cretaceous extinction, mammals were small, mostly nocturnal creatures, ecologically marginal compared to the dominant dinosaurs. The largest mammals of the Mesozoic were roughly the size of a badger. Within 10 million years of the Chicxulub impact, mammals had diversified into dozens of new orders, producing whales, bats, elephants, horses, primates, and countless other lineages. Body sizes increased by orders of magnitude. Ecological strategies exploded in diversity. The entire modern mammalian fauna, from shrews to blue whales, can be traced back to this post-extinction radiation. Without the asteroid or comet that struck Yucatan, the mammalian world we inhabit today would not exist. We would not exist. This pattern extends beyond single extinction events. The entire Phanerozoic history of life, the past 540 million years of complex multicellular organisms, can be read as a series of catastrophic prunings followed by creative regrowth. Each extinction removes the dominant incumbents. Each recovery allows previously marginal lineages to experiment, innovate, and diversify. The result, over hundreds of millions of years, is a biosphere of increasing complexity and diversity, one that has been repeatedly shattered and rebuilt, each time reaching new heights of ecological sophistication. The process is brutal and wasteful by any moral standard, but it is also, viewed from a sufficient distance, creative in a way that no purely gradual evolutionary process could be. There is a deep irony here. The same process that destroys also creates. The comets that Gliese 710 may one day send toward Earth could cause unimaginable destruction, but they could also, in the long run, create the conditions for something new and perhaps extraordinary to emerge. This is not a consolation in any practical sense. The timescales are far too long for any individual or civilization to benefit from the creative destruction of mass extinction. But it does suggest that the cosmic bombardment cycle is not purely destructive. It is, in some sense, a necessary ingredient in the evolutionary process that produces complexity, intelligence, and perhaps even awareness of the process itself. Consider the strangeness of our situation. We are a species that exists, at least in part, because of past cometary bombardment events. The Chicxulub impact cleared the ecological stage for mammalian diversification, without which our lineage might never have emerged. And now, using instruments of extraordinary precision, we have detected the approach of a star that may trigger the next such bombardment event 1.3 million years in the future. We are the products of past cosmic violence, using our intelligence to predict future cosmic violence. We are the Oort Cloud's consequences, watching the Oort Cloud's future unfold. This recursive quality, this strange loop, in which the observer is also the product of the process being observed, gives the Gliese 710 story a philosophical dimension that transcends its scientific content. It forces us to confront the question of perspective. On what timescale should we evaluate the significance of this event? On a human timescale of decades or centuries, the encounter is irrelevant. Gliese 710 will not arrive for over 1 million years. Nothing will change in our lifetimes. On a geological timescale of millions to billions of years, the encounter is one in a long series, a recurring beat in the rhythm of galactic perturbation that has shaped the solar system since its formation. On a civilizational timescale, the question becomes more complex. Will human civilization, or whatever succeeds it, still exist in 1.3 million years? If so, will it have the technology to defend against a comet shower, or will it have long since disappeared, leaving the Earth's biosphere to face the bombardment unprotected, as it has faced every previous one? These questions have no definitive answers. They lie at the intersection of astronomy, evolutionary biology, and speculative philosophy. But they are worth asking because they illuminate something important about the human condition. We are temporal beings. We live in the present, worry about the near future, and struggle to comprehend timescales that dwarf our experience. A million years is an abstraction. 1300 centuries is a phrase that sounds meaningful, but is essentially impossible to viscerally grasp. We cannot feel the weight of that time. We cannot imagine the generations that will live and die before Gliese 710 reaches its closest approach. We can only calculate and predict and wonder. To put the timescale in perspective, consider what 1.3 million years means in human terms. Modern Homo sapiens has existed for roughly 300,000 years. All of recorded human history, from the earliest Sumerian cuneiform tablets to the present day, spans roughly 5,000 years. The interval between now and Gliese 710's closest approach is therefore roughly 260 times longer than all of recorded history. It is roughly 4 times longer than our entire species has existed. Whatever walks the Earth when the comet shower arrives will almost certainly not be Homo sapiens as we know ourselves today. Evolution does not stop. In 1.3 million years, natural selection, genetic drift, and perhaps deliberate biotechnological modification will have transformed our descendants into something unrecognizable if our lineage survives at all. The comet shower that Gliese 710 triggers will strike a world populated by beings we cannot imagine, living in societies we cannot predict, facing the bombardment with capabilities we cannot foresee. There is something both humbling and liberating in this realization. Humbling because it reveals the absurdity of worrying about an event that lies so far beyond our temporal horizon. We will not live to see it. Our children will not live to see it. 1,000 generations of our descendants will not live to see it. Liberating because it frees us to appreciate the encounter for what it truly is. A magnificent natural phenomenon, a piece of the galaxy's ongoing self-expression, played out on a canvas of space and time so vast that human concerns shrink to insignificance against it. And yet we do wonder. That is itself remarkable. Among all the species that have ever existed on Earth, totaling perhaps 5 to 50 billion over the planet's history, we are the first to look outward and detect an approaching star. We are the first to model the Oort Cloud, to compute orbital perturbations, to predict comet showers millions of years in advance. We are the first to understand, even imperfectly, the causal chain that connects the motions of distant stars to the fates of species on this small rocky planet. The fact that we can comprehend this chain is arguably as significant as the chain itself. Comprehension creates the possibility of response, prediction creates the possibility of preparation, and awareness, even of threats that lie impossibly far in the future, changes the way a civilization understands its place in the universe. The deeper truth, then, is not simply that a star is approaching the Oort cloud. It is that the solar system has never been the isolated, self-contained clockwork that our textbook diagrams suggest. It is an open system, embedded in a dynamic galactic environment, subject to perturbations from passing stars and the gravitational tide of the Milky Way. Its stability is real but conditional. Its safety is genuine but temporary, and the comets that occasionally rain down on the inner planets are not external intrusions into an otherwise peaceful system. They are internal responses to external stimuli, signals transmitted from the galaxy to the biosphere through the intermediary of the Oort cloud. Gliese 710 is simply the next messenger, and the message it carries, delivered across a journey of 1.3 million years, is the same message the galaxy has been sending since the solar system formed. You are not alone in space, and space is not indifferent to your existence. So where does this leave us? We have traced the trajectory of a single orange star through the solar neighborhood. We have mapped the ghostly reservoir of icy bodies that surrounds our solar system. We have modelled the gravitational encounter that will unfold in 1.3 million years, estimated the comet shower that will follow, and confronted the possibility that the shower could, with some small but non-zero probability, produce impacts on Earth capable of causing mass extinction. We have examined the geological evidence for past impacts and the biological evidence for their evolutionary consequences. We have assessed our capacity to defend against long-period cometary threats and found it essentially non-existent. And we have explored the deeper philosophical implications of living in a solar system that is permeable to galactic influence and subject to periodic bombardment. The question that remains is deceptively simple. What should we do with this knowledge? The most immediate and practical answer concerns the continuation and expansion of astrometric surveys. Gaia has transformed our understanding of the stellar neighbourhood, but its mission will not last forever. The spacecraft is expected to exhaust its operational lifetime sometime in the late 2020s, though extensions may push this to the early 2030s. After Gaia, the question is what comes next. The astronomical community has proposed several successor missions, each designed to push astrometric precision even further and to cover wavelengths and types of objects that Gaia cannot see. Infrared survey telescopes, for example, could detect the brown dwarfs and very low-mass stars that are invisible to Gaia's optical instruments. A complete census of stellar and substellar objects in the solar neighbourhood would dramatically improve our understanding of the encounter environment, allowing us to identify potential close approaches that are currently unknown. The importance of this work extends far beyond the Gliese 710 encounter. As we have seen, Gliese 710 is the most significant known future encounter, but it is almost certainly not the only one. The stellar census is incomplete, and the missing entries are precisely those objects that are hardest to detect: faint red dwarfs, brown dwarfs, rogue planets, and stellar mass black holes. Any of these could pass close to the Oort Cloud without our knowing, and some of them may have done so in the relatively recent past. A complete inventory of nearby moving objects is therefore a matter of both scientific interest and, in the very long term, planetary safety. Beyond astrometry, the Gliese 710 encounter underscores the need for continued research into the structure and population of the Oort Cloud itself. We have never directly observed a single Oort Cloud object in situ. Everything we know about the cloud is inferred from the comets that emerge from it, supplemented by theoretical models of solar system formation and evolution. This is like trying to characterize an iceberg by studying the droplets that occasionally melt off its surface. The inferences are useful, but profoundly incomplete. A future mission to the outer solar system, perhaps a deep space probe traveling beyond the heliosphere and into the inner Oort Cloud, would provide the first direct data on the population, composition, and spatial distribution of Oort Cloud objects. Such a mission is technologically daunting, but not impossible. Current propulsion concepts, including solar sails, nuclear thermal propulsion, and gravity assists, could in principle deliver a small probe to distances of 1,000 or more astronomical units within a human lifetime. The scientific return would be enormous, providing ground truth for the models that currently underpin all of our predictions about the effects of stellar encounters. We should also consider the broader planetary defense implications. As we discussed in the previous section, our current ability to detect and deflect long-period comets is virtually non-existent. The Gliese 710 encounter will not produce its comet shower for millions of years, but the architectural gap it exposes is relevant right now. Even without Gliese 710, long-period comets can arrive from the Oort Cloud at any time, dislodged by the steady background perturbation of the galactic tide and past stellar encounters. The long-period comet warning problem, as it might be called, is a gap in our planetary defense posture that predates and will outlast any single stellar encounter. Addressing this gap would require investment in wide-field infrared survey telescopes, optimized for detecting faint objects at large distances from the Sun, rapid response mission architectures capable of deploying deflection assets on timescales of months rather than years, and research into deflection technologies that work against fragile, volatile-rich targets rather than solid rocky asteroids. The Gliese 710 encounter provides a compelling scientific justification for this work, even though the encounter itself lies far in the future. There is also a broader institutional question. Who is responsible for monitoring and preparing for threats that unfold on million-year timescales? No existing government or international organization has a mandate that extends to such time horizons. The longest-term planning efforts in human civilization, those related to nuclear waste storage, for example, typically address timeframes of 10,000 to 100,000 years. Even those efforts are controversial and uncertain. Planning for an event 1.3 million years in the future is so far beyond any institutional time horizon that it borders on the absurd. And yet the event is real. The physics is certain. The only question is whether any institution will exist long enough to translate understanding into action. There is also a lesson here about the nature of scientific prediction and the limits of certainty. The Gliese 710 encounter is sometimes presented in popular media as an impending catastrophe, a cosmic collision that will devastate Earth in a million years. This framing is misleading. What we can say with confidence is that the encounter will occur, that it will perturb the Oort Cloud, and that the perturbation will increase the rate of long-period comets entering the inner solar system. What we cannot say with confidence is whether any of those comets will actually hit Earth, or whether any impact that does occur will be large enough to cause significant damage. The probability chain is long, and at each link there are uncertainties that propagate and amplify. The encounter is certain. The comet shower is very likely. A significant increase in impact probability is probable, but a specific catastrophic impact on Earth is not predicted with any confidence. It is a possibility, not a certainty. This distinction matters because it reflects a broader truth about how science handles risk over extreme timescales. We are accustomed to thinking about risk in human terms over decades or lifetimes. Insurance companies calculate the probability of house fires and car accidents with great precision, using actuarial data accumulated over centuries. But when the timescale extends to millions of years, the tools change. We are no longer working with actuarial tables. We are working with physical models, computational simulations, and statistical extrapolations, each carrying its own assumptions and limitations. The resulting risk estimates are genuine but approximate. They describe a landscape of possibilities rather than a single definite outcome. This is not a failure of science. It is a feature of the problem itself. The solar system is a chaotic dynamical system in the mathematical sense. Small differences in initial conditions can lead to vastly different outcomes when projected far into the future. The orbit of a specific Oort cloud object 1.3 million years from now cannot be predicted with precision because infinitesimal uncertainties in its current position and velocity are amplified exponentially over time. What can be predicted with reasonable confidence is the statistical behavior of the ensemble, the total number of objects perturbed, the average increase in cometary flux, the probability distribution of impact rates. These are the quantities that matter for risk assessment, and they are the quantities that researchers have been working to constrain. The appropriate response is not panic and not dismissal, but informed vigilance. We should continue to study the encounter, refine our models, improve our surveys, and develop the technological capabilities that might one day allow a civilization to defend itself against long-period cometary threats. And we should do so with the humility that comes from knowing that our predictions, however sophisticated, are approximations to a reality that is vastly more complex than any model can capture. There is one more implication worth dwelling on, and it is perhaps the most important of all. The Gliese 710 encounter reminds us that the universe operates on time-and spatial scales that are fundamentally alien to human experience. We evolved to navigate a world measured in meters and years, in the immediate dangers of predators and weather and disease. Our intuitions are calibrated to these scales. They serve us well in our daily lives, but they fail utterly when confronted with the realities of astrophysics and geology. A million years is not a long time on the cosmic scale. It is a blink. And 13,000 astronomical units is not a long distance on the galactic scale. It is a whisper. The forces that will reshape the Oort Cloud and potentially redirect the evolution of life on Earth are gentle by cosmic standards, slow by human standards, and inexorable by any standard. This encounter between human timescales and cosmic timescales is in many ways the central drama of the Gliese 710 story. We have discovered something real and significant, something that will genuinely happen, but we have discovered it so far in advance that we cannot meaningfully prepare for it or prevent its consequences. We are in the position of someone standing on a beach, watching the first faint swells of a tsunami that will arrive in 100 years. The observation is scientifically valuable. The prediction is genuinely useful, but the response, for now, can only be understanding, not action, and perhaps that is enough. Perhaps the greatest value of the Gliese 710 discovery is not what it tells us about the future, but what it tells us about the present. It tells us that we live in a dynamic galaxy, that our solar system is part of a larger gravitational ecosystem, that the peace and stability of our planetary environment is a temporary condition maintained by the fortunate absence of close stellar encounters, and that this peace will, eventually, be disrupted again. It tells us that we are connected, through gravity and time and the slow migration of icy bodies, to stars we cannot see with the naked eye, and to events that will unfold long after our civilization has ended or transformed beyond recognition. It also tells us something about the value of pure scientific inquiry. The Gaia mission was not designed to find threats to Earth. It was designed to map the Milky Way, to understand the structure and evolution of our galaxy, to answer fundamental questions about stellar populations and galactic dynamics. The discovery of Gliese 710's close approach was a secondary finding, a consequence of the extraordinary precision of the astrometric data, rather than a primary mission objective. This is how science often works. The most consequential discoveries emerge not from targeted searches, but from systematic observations conducted with sufficient care and precision to reveal patterns no one anticipated. The case for funding and supporting basic research in astronomy, astrometry, and planetary science rests not only on the specific threats it might uncover, but on the broader understanding it provides of the environment in which our planet exists and the forces that have shaped and will continue to shape its destiny. This is not a cause for fear, it is a cause for wonder. Right now, at this very moment, Gliese 710 is out there. It sits roughly 62 light-years away in the constellation Serpens Cauda, shining with the dim, steady glow of an orange dwarf star, too faint for the naked eye, but easily visible through a modest telescope. It looks unremarkable. It looks like any of the millions of faint stars that populate the background sky. Nothing about its appearance suggests that it is anything other than an ordinary member of the stellar population. And yet this ordinary star is moving. It is moving toward us. Not quickly, by human standards. Not in any way that we could perceive, even if we watched for a lifetime. The angular motion across the sky is so small that it would take centuries to notice without instruments. But the radial motion, the approach directly along the line of sight, is relentless. 24 kilometers every second, 86,400 kilometers every hour, just over 2 million kilometers every day, roughly 750 million kilometers every year. This has been happening since before our species existed and will continue long after anything recognizable as our civilization has ended or evolved beyond recognition. In roughly 1.3 million years, Gliese 710 will reach its closest approach to the Sun. It will pass through or near the outer regions of the Oort Cloud, at a distance of approximately 10,000 to 13,000 astronomical units. At that distance, it will not be visible as a star in the traditional sense. It will be a brilliant point of light, perhaps reaching an apparent magnitude of -0.5 to -1, brighter than any star currently visible in the night sky except Sirius. For a few thousand years around closest approach, it will be one of the brightest objects in the heavens, a new star that our distant descendants, if they exist and if they look up, will see blazing in a constellation whose shape will have changed almost beyond recognition from the patterns we know today. And then it will recede. It will continue on its trajectory through the galaxy, moving past the Sun and away, back into the vastness of interstellar space. Within a few tens of thousands of years of closest approach, it will have faded back to invisibility, just another faint star among billions. The encounter itself will be brief by cosmic standards, a gravitational handshake lasting perhaps a few thousand years at most. But its effects will linger for millions of years, as the perturbed comets slowly spiral inward from the Oort Cloud, threading through the orbits of the outer planets, and eventually reaching the inner solar system. The comet shower will build gradually, imperceptibly at first, then growing to a peak perhaps 1 to 2 million years after the encounter. For a period of several million years, the night sky of Earth, or whatever world our descendants inhabit, will be graced by more long-period comets than usual, bright visitors from the outer dark, each one a messenger from the disturbed edge of the solar system. Most will pass harmlessly by, arcing around the Sun on their elongated orbits and disappearing back into the darkness. But some, a few among millions, may come close enough to threaten a planet, and one, if the probabilities align in a particular and unfortunate way, might strike. We cannot know whether that will happen. The probabilities are small but non-zero. The timescales are so vast that prediction becomes a matter of statistics rather than determinism. What we do know, is that the encounter is coming, that the physics is real, and that the process has been repeated countless times in the solar system's 4.5 billion year history. This is the rhythm of the solar system, not the clockwork regularity of planetary orbits, which cycle with reassuring precision year after year, but a deeper, slower rhythm, one driven by the passage of stars through the solar neighborhood, the gentle tide of the galaxy, and the ancient reservoir of icy bodies that surrounds the Sun like a diffuse halo of potential. This rhythm is not regular. It is stochastic, driven by the random walks of stars through the galaxy and the chaotic dynamics of gravitational perturbation. But it is real, and it is persistent, and it has been playing since the solar system formed. The comets that occasionally appear in our skies are echoes of this rhythm. Every bright comet that blazes across the sky, every long-period visitor that arrives unannounced from the outer solar system, is evidence that the Oort Cloud exists, that it is being perturbed, and that the processes we have described in this video are actively occurring right now. We do not need to wait 1.3 million years for Gliese 710 to arrive. The Oort Cloud is being stirred at this moment by the galactic tide and by the cumulative effects of past stellar encounters. Gliese 710 will intensify this process. It will not initiate it. There is a strange beauty in this picture. The solar system, which we often think of as mechanical and predictable, is revealed to be something far more complex and interesting. It is a gravitational ecosystem, open to its environment, responsive to external forces, capable of transmitting perturbations from interstellar distances to the surfaces of planets over timescales of millions of years. The ice of the Oort Cloud, formed 4.5 billion years ago in the same disk of gas and dust that gave birth to the Sun and planets, has been waiting in the cold dark ever since, preserved by the vacuum of space, subject to the occasional gravitational nudge from a passing star. When that nudge is strong enough, some of that ancient ice begins its long fall sunward, eventually becoming visible as a comet, that most ancient and evocative of astronomical phenomena. And we, standing on one of the inner planets, have figured this out. We have mapped the star's trajectory. We have modelled the Oort Cloud. We have estimated the comet shower. We have calculated the impact probabilities. We have connected the motions of a dim star in Serpens Cauda to the potential future of life on Earth. This chain of reasoning, stretching from astrometric measurements of stellar positions to predictions about comet showers millions of years hence, to assessments of existential risk for a biosphere, is one of the most extraordinary achievements of human intelligence. So the next time you look up at the night sky, consider this. Somewhere out there, too faint to see, a small orange star is falling toward us. It has been falling for millions of years and will continue falling for a million more. When it arrives, it will reach into the outermost edges of our solar system and gently rearrange the furniture. And then, slowly, over the following millions of years, the consequences of that rearrangement will ripple inward through the orbits of the outer planets, past Jupiter and Mars, and perhaps, one day, to the surface of the Earth itself. It is a story written in gravity and played out in ice. It spans timescales that dwarf human civilization and distances that diminish human geography to a single point. And it reminds us, with quiet force, that we are not separate from the cosmos. We are embedded in it. We are products of it, and we are subject to its processes, whether we understand them or not. Gliese 710 is coming. It does not care. It does not know. It simply follows the laws of physics, as it has done for billions of years, and will continue to do for billions more. And that, perhaps, is the most profound thing about it. In a universe that operates without purpose or intention, the approach of this star is simultaneously terrifying and beautiful, a reminder that the same indifferent forces that created us may one day reshape the world we inhabit. The star is coming, and now you know. Thanks for watching. If you found this video interesting, please consider subscribing and hitting the notification bell so you don't miss future explorations of the universe. We'll see you in the next one.